Hello everyone, we are group 14 and today we'll be speaking about tuberous sclerosis and its possible connection with autism. Overall, we'll be speaking about how an inherited gene can result in an altered signaling pathway, resulting in an observable phenotype. So autism spectrum disorders are a group of disorders affecting around 1% of the population and are characterized by behaviors such as impaired communication or abnormal social interactions. Although the cause is unknown, multiple genetic mutations involved with synapse formation are associated with ASD. While synapse formation occurs throughout the lifespan, exuberant synaptogenesis occurs in early brain development. It is thought that this growth leads to some ASDs. This theory has been studied in brain biopsies of children with and without autism and showed a much greater reduction in synapses when comparing those with and without ASD.
TSC is a genetic disease characterized by the formation of benign hamartomas. However, 40 to 50% of TSC patients also have autism spectrum disorder. Researchers believe that this may be due to malformations in the dendrites, which appear crowded and mushroom-shaped in TSC patients. This could possibly lead to issues in neuronal connectivity and impair the ability of the cell to perform synaptic pruning.
Synaptic pruning refers to the process by which extra neurons and synaptic connections are eliminated in order to increase the efficiency of neuronal transmissions. It occurs in early childhood up until adulthood. Most autism diagnoses are not diagnosed before this process of pruning begins. Synaptic pruning continues after the initial crucial period, usually from ages 2 to 10. However, it slows down and typically ends in the late 20s. Here we can see synaptic connections at birth at 6 years old and at 14 years old. Up until 6 years old, you can see the exuberant growth of neurons. Following this is the synaptic pruning, which causes the decrease in synaptic density by 14 years old. Individuals with ASDs don't have as much synaptic pruning. When discussing proteins involved in pruning, mTOR is one of the most important. mTOR is a kinase involved in multiple signaling pathways. The mTOR pathway shows that mTOR is involved with a variety of proteins, including TSC1 and TSC2.
This is the mTOR activating pathway. mTOR is a kinase. Its downstream targets initiate cell growth and synapse formation. mTOR is activated by Reb-GTP. The TSC complex stimulates GTPase activity that hydrolyzes Reb-GTP into Reb-GDP. Reb-GDP is not active and does not stimulate mTOR. The TSC complex inhibits mTOR by limiting its activator. When the cell wants to stimulate synapse formation, TSC is inhibited by a phosphorylation cascade. An inhibited TSC complex means that concentrations of Reb-GTP will be high enough to activate mTOR. Metabotropic receptors initiate this phosphorylation cascade. One receptor that activates this pathway is neurotrophic factor receptors. Neurotrophic factors, like brain-derived neurotrophic factor, stimulate neuron growth. Interestingly, glutamate receptors also activate this pathway. Glutamate is the most common excitatory neurotransmitter in the central nervous system. Neural stimulation can induce synapse formation. In tuberous sclerosis, the TSC complex is mutated. The mutant complex does not inhibit the mTOR pathway as well as the wild type. This can lead to excessive synapse formation.
So in conclusion, the inherited TSC mutation causes an altered signaling pathway in which there is an overactive mTOR. This overactive mTOR, which is involved in synaptogenesis, is believed to cause excessive synapses and prevent the cell from performing synaptic pruning, which may lead to increased risk of developing an ASD in TSC patients. We hope you learned something new throughout this presentation, and thank you, Professors Pack and Stratton, for a great semester.